let's go through the solubility rules, which if you have the book, you should probably go to page 330, table 8.1, which has a nice summary of the solubility rules, and you should memorize them. And they basically tell us if an ionic solid is soluble or not, meaning in water, of course, aqueous solution. So it will tell us whether sodium chloride will break into sodium and chloride ions and be a strong electrolyte. And so this is why these solubility rules are important. So we can predict reactions and potential precipitations or acid-base reactions. We can do this all based on the solubility rules. Okay, so rule number 1, group 1A and ammonium compounds are soluble. No exceptions. This is a good one. This is a pretty easy one. Rule 1 and number 2 are all ions that are always soluble, no matter what. No exceptions. And so those are good to know. Group 1, of course, is lithium, sodium, potassium, rubidium, and cesium. For all practical purposes, it's going to be lithium, sodium, and potassium. Those are the three that are most common and that you will encounter in most chemistry classes. And then ammonium, which is a polyatomic ion. And you should know the polyatomic ions, right? So you may be able to access in your book the solubility rules, but if you don't know what phosphates are and sulfates and ammonium, so at some point cutting corners is just going to break down. All right, so no exceptions, right? So that means that no matter what I put lithium with, like lithium hydroxide, and there's a rule later on that says hydroxides are insoluble. But if I know that lithium is always lithium, ammonium, potassium, if I know this group 1, this rule 1, that everything always is soluble, then I don't even have to know the rule for hydroxide. I can just say it doesn't matter what the rule is. The exception is always true, that lithium hydroxide will be soluble. And the same is true for acetates and nitrates. Now acetates are CH3, CO2 minus. We just talked about it, acetic acid and acetate. It is written as C2H3O2 minus in this book. These two are interchangeable. This just gives you more structural information. And it indicates that there's this group that makes it acidic here, right? That if it binds with H+. And then of course nitrates, NO3. So this is good. And you got to know the charges, right? So that you know that when nitrate binds to lithium, it's going to be in a 1-to-1 ratio, and if it binds with calcium, it's going to be in a 1-to-2 ratio, right? That's important that you remember the charges and you remember how to put ionic compounds together. Rule number 3, most. Okay, so most now indicates that there are exceptions. Most chlorides, bromides, and iodides, which are the halides in group 7. So we're talking about chloride, bromide, and iodide. Those are soluble, especially with lithium and ammonium, right? But there are some exceptions. And those are silver, lead, and then mercury. But this isn't just regular mercury. It's a little weird. And it's almost like a polyatomic ion. It's an Hg2 plus 2 ion. Okay, so that's going to be important to note. If you see mercury so Hg2 Cl2 solid, right? So that's an interesting formula. You normally wouldn't see that, but this is because that's a polyatomic ion, Hg2Cl2, right? So that would precipitate. That would have a solid. That would not be soluble. It would not be an electrolyte. Next rule, most sulfates, SO4 minus 2, are soluble except for calcium, strontium, barium, lead, and silver. So lead and silver here come up again, right? We had lead and silver here not being soluble, and so lead and silver are not very soluble unless they bind to certain polyatomic ions that are always soluble, such as nitrate, for example, right? So, but they come up again, and then calcium, strontium, and barium is going to come up again later on. But for the sulfates, those are the ones that are going to precipitate. Those are the ones that are not strong electrolytes, right? Sulfates, SO4. So calcium sulfate is insoluble, but sodium sulfate and copper sulfate, iron sulfate, any other metal you want to throw at sulfate is going to be soluble. And then we have a whole bunch of insoluble ions. The carbonates are insoluble, the phosphates are insoluble, the sulfates are insoluble, the hydroxides are insoluble, right? So those are all insoluble. And look at every time it's going to be that group, that rule 1, and that's going to be the exception. That 1A and ammonium. These are insoluble except 1A and ammonium, 1A and ammonium, 1A and ammonium. Again, 1A and ammonium. So that's always good to know, right? But then carbonates, CO3 minus 2 are insoluble, and phosphates, PO4 minus 2 are insoluble. So in a way, this can be lumped into one rule. Really, carbonates and phosphates are insoluble except for those. And group 7 and 8 can be lumped into one. They have these other ions that are soluble here, right? Calcium, strontium, and barium. So sulfides, which is IDE, right? Remember, single element is S minus 2. Don't confuse them with the sulfates, right? Sulfates are soluble. Sulfides are insoluble. And then to make matters worse, we have calcium, strontium, and barium that are the exception, which was also the exception for the sulfates, right? Except the sulfates are soluble, and so the exceptions are insoluble. Here it's the other way around, so that makes it a kind of confusing, but that's just something you're going to have to figure out, right? So sulfites and hydroxides. You have the calcium, strontium, and barium that are soluble, and then of course group 1A and sodium. And so the hydroxides are special. Remember Arrhenius acids and bases. Hydroxides, those compounds that produce hydroxides in solution are Arrhenius bases. And so any soluble hydroxide, so let's just say sodium hydroxide, is a strong, it's a strong base, right? Because it breaks apart completely into sodium and hydroxide ions. And that's what it means for these solubility rules. If you have something that's soluble, it will break apart into its ions. And if one of those ions is a hydroxide, you got a strong base. If one of those ions is a proton or H+, you have a strong acid. But let's get back to that. Here's a nice little table with exactly those rules summarized. This is what you have in the book. I recommend that's what you look at to do the next few pages. So here we are again, sodium, potassium, and lithium and ammonium, always soluble, no exceptions. Nitrates and acetates, no exceptions. Here are the halides, right? There's that rule. So here we have like the soluble ones with exceptions. Here we have the insoluble ones. So they have those four. They lumped hydroxides and sulfides together because they have the same exceptions. And they lumped the carbonates and phosphates together. Okay, so let's take a look at certain compounds and use the solubility rules. Here I'm just asking you, okay, lead chloride, is it soluble or insoluble? Okay, so got to find the rules, got to remember, right? So this is about the halides here. The halides are all soluble, but let's see, is lead one of the exceptions? Yes, it is. So this is going to be insoluble. So that's important that you can fish this out and figure this out. Let's go to B, copper chloride. Okay, same rule. The chlorides are all soluble. Copper is not an exception. So therefore it is soluble. I don't remember. What did I say? Soluble, right? All of those are soluble except lead, silver, mercury. Copper is not part of that. So it's got to be soluble. And then again, that means that we get copper and 2 chloride ions. And another thing that's important is that you realize that 2 is there, because that must be copper 2 chloride. So this is a plus 2 ion. So this breaks into copper ions and 2 chloride ions. And so that's also important. Nitrates are always soluble. Don't have to worry about it. There are no exceptions. Always soluble. Sulfates are soluble except for, let's go look. So sulfates are soluble except for calcium, barium, lead, silver, and strontium. So what we have here is we have an insoluble because it's one of the exceptions, right? Nickel sulfate, sulfides are soluble. They're insoluble, and so therefore it's insoluble. Magnesium phosphates. Phosphates are insoluble. Magnesium is not one of the exceptions. Lithium carbonate. Carbonates are insoluble, but that's group 1, so that's always going to be soluble. So that group, that rule 1 beats that. This is double soluble, right? Ammonium, no exceptions, always soluble. Chloride, always soluble. Not always, has exceptions. Silver, lead, and mercury, right? So there's that. And I'm going to say it one more time, what it means for a substance to be soluble, like NH4Cl. In an equation, that means you are going to put the symbol AQ next to it. AQ indicates that in reality, we have ammonium and chloride ions in solution, right? They're free-flowing, you can conduct electricity, right? So here's an example. Here are 2 soluble ionic solids. Potassium iodide, indicated by AQ. Don't even need to look at the periodic table. No, I mean of course, the solubility rules, right? So here is lead nitrate, also aqueous soluble. And above is a beaker showing what happens in solution. You don't have Ki together. It's not sticking together. These are free-flowing, moving. This potassium ion can move over here without the chloride iodide following, right? So you have these anions and cations that are free-flowing. You can send electricity through this. This is a strong electrolyte, and the same is true for silver nitrate. All nitrates are soluble. So here's nicely shown. In the center, you've got the nitrogen. On the outside, you have 3 oxygens. So that's the polyatomic ion here. Here's 3 of them, 4 of them, sorry, and 2 lead ions. And as I said again, these are free-flowing. You can look at this. It's a homogeneous mixture. You cannot see silver nitrate ions and lead ions, and you just can't see them, right? What happens when you pour these 2 liquids together? Initially, you have potassium iodide and lead nitrate aqueous, right? So we would write this in a reaction like that. We would write this and that is reacted together. Well, does a reaction occur, okay? So what we look at is these can all bounce into each other now, right? And so according to the solubility rules, the halides are soluble except for lead compounds, silver, lead, and mercury. So when that iodide bumps into a lead, it's instantly going to precipitate into this beautiful yellow solid. And so the reaction that occurs, and that's indicated here. So that's going to form a solid. That's going to go back to its crystal lattice and tie up the lead and iodide ions. But the potassium and nitrate ions are unaffected. Okay? So what happens here, you just got to check, and that's what this crisscross is trying to do here, right? So initially you had lead nitrate and potassium iodide. Now, if you exchange these two, would a reaction occur? So that's what you have to think about, right? So if I ask you to predict the reaction between potassium iodide and lead nitrate, you just have to write it down like this. Ki, look up or know that this is aqueous. Phase label, very important, have to have it. And you have lead nitrate, which is also, according to the solubilities, it's soluble. And then you have to ask yourself, what would happen is this crisscross thing here, right? If you exchange potassium and nitrate and iodide and lead, and then you realize that, okay, so the exchange product PBI, and so PB is plus 2, right? And I is minus 2. So the actual proper formula is PBI2. That would form a solid. And the other two ions, and so this is really just here already, right, is still aqueous. So you have KNO3 AQ. So that would be the molecular equation here. And this is what that looks like. All right, if I dumped a solution of potassium iodide into a solution of lead nitrate, you would see this yellow precipitate. And that is that silver iodide that's being formed and precipitating out. That is called a precipitation reaction. And this entire equation is called the molecular equation. All right, and so let me go back here. Right, so we have the molecular equation. Let me use this as an example. What you can also do is you can write the ionic equation, which shows us what's actually happening in solution, and it helps us understand why a reaction occurs. So you have Ki and I and nitrate and Pb, and those are actually as ions. So you have K plus and I minus and Pb. I'm just copying it down. And then I have two nitrates, right? I have 2NO3 minus, right? And that's because I have that 2 here. And so then what happens is we form a solid, PbI2, right? So we're going to actually need, if we balance that, we're going to need 2 of those. And that's a solid. But the other product that forms for a complete ionic equation, we actually still have K plus. It doesn't change anything, and NO3. They're still ionic. We have 2 of each of these. And so now if you look at that, we have K potassium ions on the left, and we have potassium ions on the right. That's called a spectator ion. Those two don't participate in the actual chemistry that's happening. So they can actually drop out for us to determine a so-called net ionic equation. What we're writing here is a complete ionic now. And the same is true for nitrate. Those two nitrate ions are non-participating. They're called spectator ions. And so in the end, what we have is we have a net ionic equation. I'm going to write it above, way above. And that's simply lead ions reacting with iodide ions to form lead iodide. And that makes a solid. That's a precipitation reaction. That's a net ionic equation. Okay, so let's take a look at this vocabulary we just learned and use a different example. Here we have silver nitrate and sodium chloride. Essentially the same rule, right? Instead of lead we have silver, and instead of iodide we have chloride. And so it is that halide rule. Chloride, iodide, and bromides are soluble, right? Except for silver, lead, and mercury. So instead of lead, we use silver here. Same idea. We get silver chloride precipitating out. And that's a white solid, actually. So silver chloride is a white solid. And so for you to be able to write this, you just need to determine whether it's aqueous or not. So silver nitrate aqueous, sodium chloride aqueous, and then determining what precipitates out, if any. If all of this was aqueous and we had no reaction, you would write an R instead of the products here. But here we have a precipitation reaction. So this is the whole thing is the molecular equation. You've completed it. It's easiest to see. Then we can write a complete ionic equation. So all you do is you take all of the aqueous compounds and you break them up into ions. So silver nitrate will break into silver and nitrate ions. And you can just leave the phase labels out. Having the charges, the ions there, indicates that they are aqueous. So we have silver ions, lead, nitrate ions, sodium ions, and chloride ions, all in solution. And then, all right, we have this stays together as a solid, so we don't break that apart. The little S indicates that, but this is aqueous still. So you have sodium and nitrate ions. That's called the complete ionic equation. That's what we see down here. And then the net ionic equation simply eliminates the spectator ions. So nitrate on the product side and the reactant side will drop out. Sodium on the product and the reactant side will drop out. And we end up with a net ionic equation, this one right here. That's called the net ionic equation. Those is the silver and the chloride ions that bounce into each other and precipitate out. Spectator ions, again, are those ions that don't participate, nitrate and sodium. And okay, I think we are almost ready to practice. There are a couple of instances when I will ask you to write an equation that involve the hydrogen and hydroxide ions. Okay, so precipitation reactions we now understand. We're going to have two soluble ionic solids producing an insoluble ionic solid and a soluble ionic solid. That's basically a precipitation reaction. Something falls out of solution. You can usually visually see that. If one of those ions happens to be a hydroxide, then we have potentially an acid-base reaction. A soluble hydroxide is sodium hydroxide. So sodium hydroxide is aqueous, meaning we get sodium ions and hydroxide ions. That means, according to Arrhenius, if one of those ions produced from a solid is a hydroxide, that's a base. And bases react with acids. And also according to Arrhenius, for example, we have chlorides that are soluble, and if the counter ion, the cation here, is not a metal but a hydrogen, HCl, for example, hydrochloric acid, HCl, or acetic acid, right? And these things break into H+, that's soluble, it's a chloride that's soluble, and chloride ions. If it furnishes H+ ions in solution, that's an acid. And acids and bases react together to form water. So the net ionic equation when something like this occurs is H+ and Cl- forming, what am I doing? And OH- hydroxide, forming water. And the phase label here would be liquid because it's not precipitating, right? But it's forming the liquid, and you can't see it because your solvent is water. But that is still what's being produced here from H+ and OH. It adds to the water, and so that we indicate with a little liquid. And then in the very end of the lecture, we're going to look at redox reactions. But for now, we're going to just put them on hold. That's when electrons transfer. All right, when I come back, we are going to do a bunch of these reactions. We're going to predict what precipitates by using the solubility rules. Now the homework has a very nice set of examples where you can practice this, and you can go ahead and watch the next lecture first before you practice, or you can practice first and see if you can do it without any further guidance.